She is presently the professor of mathematics in the School of Physical Science, JNU. She has more than 30 publications with high repute, which includes publications in the Journal of Lie Theory, Transactions of the American Mathematical Society, Mathematics JScript, Israel Journal of Mathematics, Journal of Theoretical Probability, and so on. She is also actively engaged in the Indian Women and Mathematics initiatives. She is one of the executive members of these initiatives. I welcome everybody. Please, I request Monojit Sir, our president of the GB, to say something. Sir.
Yes. Hello.
Yes, you are audible.
I am audible?
Yes, certainly.
Very good morning. I am happy to know that Krishnagar Women's College Mathematics, Department of Mathematics is organizing a seminar lecture of Professor Riddhi Shah, Professor of Mathematics, Jawaharlal Nehru University, New Delhi. On behalf of Krishnagar Women's College family, I would like to welcome Professor Riddhi Shah for today for his presence in this virtual platform. I'd like to thank Principal and the Department of Mathematics and also IQAC for organizing such seminar lectures in this pandemic time. Today's topic is glimpse into the world of dynamics. We all know that mathematics is the quantitative logic on the basis of which study of matter and study of molecular sciences are possible. And in this world, nothing is static. Everything is dynamic. So, glimpses into the world of dynamics is a very pertinent and interesting topic. So, I strongly believe that all the teachers, students, the academicians present in this virtual platform will definitely enjoy the seminar lecture today. Thank you, Professor Riddhi Shah, for being here with us today. Again, I would like to thank the Department of Mathematics, IQAC, and the entire Krishnagar Women's College family for organizing such seminar lecture. Thank you so much. Have a nice day. Enjoy the lecture.
Thank you, sir. Stay with us. Principal Madam.
Yes.
I request to say, to say something.
Respected President, Governing Body, distinguished speaker and eminent scholar in mathematics, Professor Riddhi Shah, School of Physical Science, Jawaharlal Nehru University and Department of Mathematics. Respected faculty members and other dignitaries, and my beloved students. I have the privilege to welcome you all in the seminar lecture titled Glimpses into the World of Dynamics, presented by a very eminent professor and researcher, Professor Riddhi Shah from Jawaharlal Nehru University. On behalf of the KWC family, Krishnagar Women's College family, we have decided to host few lectures on different topics. The lecture will be arranged by the department itself. Now, the reason behind the arrangement of lecture was not only enlighten students into the subject, into the topic, but also enlighten and encourage the students beyond the applicability of the subject or the topic in real life, so that the students can think of the topic, not only the subject or the topic portion covered by the syllabus. They can be able to think beyond their syllabus, to think the applicability of the topic into the real life. And I'm glad that we have started with a big bang with such an with the lecture of such an eminent professor from JNU. To me, the COVID situation has introduced a big problem in our life, big depression, introduced depression among the students, but it has a golden phase also. I took the opportunity of the golden phase of COVID situation. This is only because of the COVID situation. We are now acquainted with the virtual platform, and we have been able to arrange this such a beautiful seminar on the virtual platform, and we can reach to our students in this mode. As a science student, I was introduced with the dynamics at the 12th standard, at my 12th standard class. And dynamics is, some sense, it is actually the trajectory, it's a time-dependent function or trajectory of a moving particle into a geometrical field, but where time is a variable. And when it comes into the question of variable, so there must be a parametric or non-parametric model. The model may be stochastic as well as non-stochastic. And when it is a model, then you cannot avoid statistics in estimating the parameters of the model. So it is an inferential logic which is embedded in the dynamics. Today, I'm very eager to listen the use of the topic, the use of statics, dynamics, and dynamical models into the real life, into the subjects like economics, like biology, like others, and its interdisciplinary usage. So I'll not take much time. I'd like to thank Professor Shah to be with us, to consent, for her kind consent to present the lecture. And I'm sure that it will be a great treat to our students before the forthcoming festival of Puja. Thank you all for joining the virtual seminar, and special thank to Professor Shah for her kind consent to being with us. I'll not take much time, Aurobinda. Please proceed. Thank you.
Thank you, Principal Madam. Now we can start. I request everybody to mute the microphone. After the lecture is over, we will invite questions. So if you have, anybody have any questions, so please ask after the session is over. So Professor Shah, we can start now.
Good morning, everybody. I hope you can hear me. Thank you, Professor Roy and Professor Dasgupta for kind words, and thank you, Professor Sarkar, for inviting me. It's a pleasure for me to give this talk, and especially to in a college which is specifically for women. I do work for cause for women to promote mathematics teaching and research among women in India. So it is a special occasion for me also to give this talk. I hope you can all hear me. So I'm going to talk about the world of dynamics from mathematics point of view. First, I'll give you examples, and then I will talk about little bit about mathematics related to that, to dynamics in which I work, and then I'll talk about some general problem called Illumination Problem. And I will wind up the talk with famous women mathematicians' work and women initiatives of Indian women in mathematics in India. Professor Sarkar, can you hear me?
Yes, perfectly
Yeah, okay.
audible.
Okay, thank you. So let's start with, as Professor Arindam has introduced me, I would just like to say that our mathematics program in JNU started in 2007 when I was the first mathematician to join, and we had initially, after 3-4 years, we had PhD programs, and now for last 2 years, 3 years in fact, there is a MSc in mathematics, and one batch has finished this summer, and another batch is going on. So if any of you are interested, we have a nice program in MSc in mathematics. So what is dynamics? So as your principal madam told you, dynamics is study of behavior of anything that moves or changes with time. So for example, you can study oscillating pendulum. You can also study water waves, even violent ones like tsunami, right? You can study weather patterns and do predictions. You must have heard about various cyclones in recent time, right? Which creates havoc. But if there is sufficient warning, you can reduce the bad effect of cyclones. You can also study chemical reactions. You can also study growth pattern in living organisms like amoeba, bacteria, or even in human beings, right? Or animals' growth. You can study also neuronal activities in brain, even in human brain. Or you can also study something very practical like day-to-day changes in prices of shares and stocks and do analysis. So it has effect on economy and general wealth of people and country. So dynamics could be in discrete time or in continuous time. You can study like what is happening today, tomorrow, day after, like that. And you can see the effect of the yesterday and day before and so on in backward time to current time. Or you can study continuously in time t what is happening, like motion of planets, stars, the changes in universe. It could be regular or chaotic. So let's see some examples. So for example, you can study popular growth in a specific region over time, right? You can also study spread of disease and infection in a given population. For example, in today's scenario, lots of people are studying the COVID-19 virus effect on people in specific region. They predict when the wave would be or what is happening. They also study the effect of vaccine for this, and it's a big question. So people study dynamics of spread of these infections, right? You can also study motion of a particle in a given medium or in another, say, so it could be a liquid or it could be air or it could be gas or whatever. You could study motion of a particle, which is a very fundamental thing to do. So we'll just study two specific examples now. We'll discuss two specific examples. So the one of them is Veluso Sabot Sinki reaction in chemistry. So this describes changes in chemical concentration. For example, C3 plus C4 plus couple as catalyst and citric acid as a reactant. And you can model by this reaction by diffusion type equation. So here is how it looks, and you can also see online some videos. It shows the changes. So let me just give one declaration that all the images are from web, and so I'm just acknowledging that that's what I've done. So here is another second example, which is mathematical models for neuronal activities. So you want to study how neurons work or behave, and the goal is to model how the voltage across a cell membrane changes over time, right? So, and that's how the information is passed in neurons. Hodgkin and Huxley derived equations in 1950 to describe this. And they found that neurons behave almost like electrical circuits. So example, trace from a bursting neuron related to breathing. When you breathe, you know, it expands and contracts. So the muscles expand and contract. So this is like, you know, this is a starting point, and 1 second later, that's what it looks like. So it is expanding. And this you can also model with using differential equations, as you can see here. The first one you can see the bunch of them, and the second one you see the expansion of it. So now, so I am a pure mathematician, and I'm going to talk about dynamics in terms of what we study in pure mathematics. So I have tried to make the talk very simple, and I will explain with examples what is done so that you have a better idea. Okay. So what is dynamical systems in mathematics? So it is a space X, okay? So it's a collection of points and a transformation T, okay? So which we take it as a continuous map T from X to X. So X is a topological space and T is a continuous map on X. So what is a topological space? Okay, it has some structure on it, but let's say most of you will know what is a metric space, right? You put a metric which is distant between 2 points. You define d, x, y equal to something, and it satisfies certain properties, then it's a metric. So we will take for this talk a space which has a matrix, and that gives a topological space, like those open balls of certain radius and so on, okay? And T is a continuous map. So T is continuous with respect to a metric. So you know about that. And for all practical purposes, you can take subsets of Euclidean space Rn as your space, and the actual distance gives in the Euclidean space gives you a metric, right? dxy is mod x minus y. So X could be compact, means it's a close bounded set, you know, not very large, or even if it's large, it has a boundary. And or it could be non-compact, unbounded set, like the whole Euclidean space, right? And T could be a regular map or a chaotic ergodic map. So here T could represent discrete or continuous time. So for a map T on X, the set T and X, so that is X, you apply T once, then you get Tx, you apply T 2 times, you get T square X, and so on. So Tx, Tx, T square X, T cube X, and so on is called the T orbit of X. Means you're starting with X and you're applying T several times. So it's called T orbit of X, okay? And if T is an invertible map, then the T orbit of X is the whole positive and negative part. So you also add T to the power minus nx, like T inverse X, T to the power minus 2x, and so on, okay? So if your map is invertible, you add all those. So remember, this concept is going to be used again and again. The T orbit of a point X in the space X is t to the power nx, where n could be a set of natural numbers, or n could be an integer. Okay, so all of that. So let's take, for example, a dynamical system, any metric space, and a continuous map. So I think most of you would know what is a continuous map on a metric space, right? So let's take X, for example. Your X could be a unit disk in R2 with the usual metric, right? The distance metric, in R2. So, and T is a map which is a rotation, let's say, by a fixed angle. So this rotation could be in whole of R2, but the disk is invariant, right? So let me show you a picture of a disk. Here is a picture of disk with radius R. Okay, everybody can see that. And the rotation by angle is angle theta, as you see here below in the picture, that anything on x-axis is rotated by angle theta. But not only that, any point, like on y-axis, again, you rotate by angle theta in anti-clockwise direction. So, for example, so this is the map. Txy is e to the power I theta xy, right? You're in R2, so actually your R2 is isomorphic to set of complex numbers, right? So this is a multiplication of two complex numbers. So it's multiplying cos theta sine theta and x comma y. So it's equal to cos theta x minus sine theta y and sine theta x plus cos theta y. So it is just taking a point, and if you draw a line from that point to the origin and you rotate by an angle theta, that line, then wherever that point goes on that line, that is the map. Okay, so x comma y goes to this txy. So it just rotated by an angle theta around. So naturally a disk of any radius will be invariant under that, because the points rotated just remain inside, because origin is inside and you have all the rays from origin to the boundary are inside, right? So, and the length of, so the norm of the point does not change, right? So that's why it stays inside the disk. And notice that it is actually a rotation, rotation map is, this map T is a rotation map on R2 and restricted to unit disk, and it stays, it is just like applying a 2 by 2 metric, cos theta minus theta, sine theta cos theta to any point x comma y, right? So it's a 2 by 2 into 2 by 1 metric, you get 2 by 1, right? So this is the metric which you apply and you get this. Okay, so it's just taking rotation. So this is one example. So what are distilled maps? A map T from x to x is said to be distilled if two distinct orbits stay away from each other. So what are the orbits, you know? For two distinct orbit means you start with a point x and start with a point y and take orbit of x, which is tnx, and take orbit of y, which is tny, and there is a minimum positive distance between each of, like for any fixed end, I take tnx and tny and calculate the distance between them, and I vary over all n, then there is a minimum positive distance if I am in a compact metric space. Like in the disk, if you apply Tn to a one point several times and another point several times and take distance between Tnx and Tny, same n, then it should remain, they should never go close to each other as n tends to infinity. They should not converge together to some point. They should not have one common limit point like that. So, and if you are in a continuous time, then you will call, you have Ttx and Tty. They remain at a positive distance. So because there is some kind of distance between these orbits, that's why the word distilled maps came. And who did it get introduced by? A famous mathematician, David Hilbert. So distilled maps were introduced by David Hilbert. You might have heard about Hilbert's famous problems, right? And so around early 1900, he had introduced these maps and also all those famous Hilbert's fundamental problems, and people are solving them many. And recently also there was some progress in some parts. So this is studied by many mathematicians, the distilled maps. So let's take 4 examples. On the real line R, you can take linear transformation by diagonal matrix, say R, just so it's actually one dimension. So Tx equal to Rx, where R is in R or R star. So of course, if R is 0, then everything goes to 0. So the orbit of every point just goes to 0. So that is not going to work for you in case of distilled, because then the orbits are for every point is going to just be same except for those 2 points. So this map is distilled if and only if R is +1 or -1. So if R is +1 or -1, what happens? Tx is either x or -x, and same you can keep applying T. Then Tnx is x or -x for all x in R and for all n. So T preserves the distance. What does it mean? T is an isometry, means the distance between x and y is same as distance between -x and -y, right? So the distance is preserved in this case, right? And so dxy is dtnx, tny. So when you have an isometry, the orbit will just remain at that distance x and y, right? dxy. So they can never go to get to converge to one point. So it is distilled, this map. And you can also check conversely, because if mod r is less than 1, then T contracts distance between any pair of 2 points, and the orbit of any point goes to 0, because suppose you take r equal to half and take x, so you get x, half x, 1/4 x, 1/8x, and 1/2 to the power nx, which converges to 0 for any x, right? So any 2 points I take, it doesn't matter, x and y, the orbit is going to be 1/2 to the power nx and 1/2 to the power ny, they both go to 0. So this is not a distilled map. And if you have mod r greater than 1, then you can take inverse. So T inverse x would be R inverse x, which will have modulus less than 1. So then this is not a distilled map, okay? So now let's see a description of rotation on the unit circle. We saw in the disk, right? So a unit circle is the boundary of unit disk. And these rotations are actually also isometric, because it's a map multiplying by e to the power 2 pi I theta. So when you take modulus, e to the power I theta is modulus 1, right? So let me give you an example. So this is a rotation. I am just going to give you a pictorial description on unit circle by showing an orbit of a rotation. So I start with 1 point, okay? And I'm going to do a 90-degree rotation. So 90 degrees pi/4, right? So you see, I'm going to do clockwise rotation. So this, if I start with the first point, apply T, I reach to this next point. Then I apply T again, I reach a third point. Yeah, I apply again, I reach a fourth point. So this is Tx, Tx, T square x, Tqf. And T to the power 4x is the rotation by 360 degree, right? 90, 90, 90, 90. So you come back to the same point, right? Again, you apply T to the power 5x, 6x, 7x, 8x. So you are then going in this you just have 4 points every time. From whichever point you start, you have the 4 different points depending on where you start, but orbit is just 4 points, right? So that's called periodic orbit because it just repeats itself. Now, so this is pi by 4, so that's why you got that. Now I start with what is called an irrational rotation, which is an irrational number multiplied to pi. Okay, so some are, so your theta angle is, with respect to pi, it's an theta is some r pi where r is irrational. Okay, so I start with this point, so it's little less than 90 degrees and clockwise rotation. So this is my mu t, right? Rotation by the, and you get this second one, third one, fourth one, fifth one. Then I apply again. So this is sixth one, seventh one, eighth one. No, so 1, 2, 3, 4, 5, 6, 7. This is 8. And then I apply few more times, 4th, 9th one, and then this. So this is third cycle. Now, if you keep doing this, what will happen is that it never comes back, the T orbit never comes back to same point, but slowly it almost fills up this circle. Unit circle, it just almost fills up. Means you keep going close to, for different values of T, you keep going close to every point. Means you, given a point, there is a subsequence nk such that T to the power nkx converges to that point. Okay, in a metric space, you know, convergent subsequence, right? So the orbit has subsequences which converges to different points, and all of them. In fact, so this is called dense orbit because it goes everywhere close. It fills up the unit circle densely. It never goes back to same point, but it can converge to that point. It can converge to any point no matter where you start from. So it's called dense orbit. So you have periodic orbit, you have dense orbit. So it fills up the space densely. Here the space is S1 unit circle. Okay. So this is how it happens. Okay. So I've just shown 4 cycle and it's a heuristic description just to give you an idea. But if you do more and more, you will get more and more, and you can mathematically show this. It's not very difficult to show it. Okay. You just need to know. So S1 is R by Z, right? Isomorphic to R by Z, and then you have to do various things. Because it's irrational, no multiple of it is going to be rational, and you can do things with that. So recall orbits. Orbit is a map, T on X, and T orbit of X is T to the power nx, or T to the power, where n is a natural number or integer, if T is invertible, or Tx, where T is a continuous time parameter. So if T is ergodic, so you saw these irrational rotations, those are an example of an ergodic map. Means basically it fills up everything. Like if you have a solution of some chemical and you add some other chemical, it will fill up, like it will go everywhere, right? The particle of the second solution will also go everywhere, right? So that's kind of movement of a particle is like ergodic. You can also so it's like, you know, every point when you apply T, it interacts with every other point or goes close to a neighborhood of every other point and so on. So that is one example of ergodic maps. So rotations are, because they are isometric, rotations are distilled maps, but when it's irrational rotation, it's distilled and ergodic. But this does not happen in most of the places. Most of the maps, especially if you have your map is a group, space is a group, and your map is a homeomorphism and a group homomorphism, then that doesn't happen. but so that the map is distal and ergodic, that does not happen. But in rotation case, it does happen. So if your map is ergodic, then the orbit is dense, like in irrational rotation. Okay, at least one orbit is dense. And a set B is dense in X if the closure of B, so means you take a set and all its limit points, that is whole space. That's what is dense. Take a set D and take all its limit points. Okay, so what are limit points? It's you take any sequence in that and take its limit points. Those are called limit points of the whole set. Then if you take all this space and its limit points together, that should be whole space, then it's called dense in that. So B is dense in X is the definition for that. And in case of irrational rotation, we saw that every orbit is dense in the circle. We saw means I just showed you as a picture, but it can be shown easily. So let's take another example. So an example of the torus. So what is torus? Torus is like a ring or surface of a donut. If you have eaten a donut, there is a hole in the middle, and it's a round ring. It's also like mendu vada looks like that. I don't know what you have in Bengal, which is close to that, but I'll show you a picture. So a torus is a product of two space, S1 cross S1, and it looks like a surface of a donut. And I'll show you a picture. So consider the map T R comma S as RS comma S, where R and S belongs to S1, and the map will twist in some sense. I'll show you a pictorial description. So here what happens is the S just remains constant, right? So only the R part changes by an angle of S. So any orbit is, so if I take RS, the orbit is containing S1 cross S. So, and the orbit could be periodic if your R is a finite order, or it could be dense. So if R is a rational multiple of pi rational rotation, then it will be periodic, and otherwise it's dense in S1 cross S. I mean S. If S is rational or irrational, that is what happens. So if S is irrational, every orbit is dense. If S is rational, then every orbit is finite. So in particular, you don't get an orbit which is dense in S1 cross S1. And this is an example of distilled map. And of course, no orbit is dense, so it's not ergodic. And actually, Hilbert introduced these maps to study non-ergodic maps. So we will see a picture on actually it's not called double torus, it's just called a torus. Double torus is different. So you see here, this is a donut, means this surface is isomorphic to the space S1 cross S1. You can see one S1 going inside out of this ring, right? So one S1 is called, it goes in and out, and the other S1 goes around the ring like this. You can see those also, right? S1, you can see those. So if I apply my T, depending on where I am, it would just go. So if I apply my T, these circles are kept invariant, but every time I apply my T, depending on where I am, it'll get moved little bit. So for example, if I am at this point where there is 1, 0, then everything remains where they are. So S is 1, so 1, 0, so you multiply it, just RS goes to RS. If I am here on top, then it would rotate by 90 degrees. And if I'm here on side, then it will rotate by 180 degree. All points will rotate on the circle by 1, and here it will rotate by 270 degrees, and so on. So depending on what S is on this big circle, it will rotate when I apply T once. If I apply more times, it will rotate more and more. So basically, if I take this great circle around like this, you can see my cursor, okay? Then it would get rotated and it would come back to itself at this point here. So let me show you a picture. Next, what happens to this great circle if I apply T once? So it looks like this, you can see. So this is just a heuristic picture. So if you cut it around, it goes around and comes back to itself. So this is another heuristic picture. So in particular, if you cut this ring and you rotate slowly, 360 degree and you patch it back, then that is what is your orbit, okay? Everybody can hear me?
Yes, ma'am.
madam.
Clearly.
Okay, good. Do you have any questions so far, or you want me to leave the questions at the end? If somebody has a pressing question, they can ask me.
Better
Okay,
to
so,
wait
huh?
till the end.
Okay, fine, thank you. So if I cut this circle on here at this 1, 0 point, then here if I cut the circle, then it becomes a hollow tube, right? And if I twist it and give total final 360 degree and join it back at same points, then I will get that how the, so suppose I draw a great circle here and then I do this cutting and twisting and joining. Then the great circle will go around like this on the side here, then it will go under, come back up, okay, here, and it will join back here like that. So it goes around this. So this is one T application of T. This is a few. So it's maybe 8 times you do. Then of course it remains round. These lines are to signify how the, if I apply T 8 times, how a point here say has moved, it goes like this, like this, like this, like this, like this, and so on. Means if I take a circle, then it twist, I mean it goes around like that. That's why I said twist in a quote. So this is what, so now so this is the dynamics on compact spaces. I gave you some example. Now I will tell you about topological groups. So this S1 cross S1 is a topological group. S1 is a topological group with complex multiplication. You multiply 2 points with same modulus, you get the same modulus in complex number, right? So S1 is a group, okay? And the point 1, 0 is the identity in S1. R is a group with addition, right? Rn is a group with also addition, right? So a group G is said to be a topological group if it admits a topology. Let's take a metric space instead of topology, under which these maps group operations are continuous. Means you take in R, x comma y going to x plus y is continuous, right, from R2 to R, and x going to minus x is continuous when you take usual distance metric, right? Everybody knows that real line, these operations, x going to minus x is a continuous map, right? And x comma y going to x plus y from R2 to R is a continuous map, right? So R is a group. Similarly, Rn is a group. S1 is a group with complex multiplication. And then if you have a group, you can take products with product topology and so on. And you get that S1 cross S1, the torus is a group, S1 cross S1 cross S1 and so on. You can do coordinate-wise group multiplication. So you get, so if you have a group and you can take product, then it is a group, right? So coordinate-wise group operations you can do, and it's a group. Then what is GLNR? It's a general linear group. So n by n real invertible matrices is a general linear group. It is a group because you can multiply and you get inverse, and you can so the group operation is multiplication of two matrices, and you know how to take inverse when the map is in the metric is invertible, right? So that's called GLNR. It can be embedded in Rn square, right? Each entry wise embedding, and you get a topology, the distance metric topology from Rn square to this GLNR. Similarly, SLNR, special linear group, is the invertible matrices of, so matrices of determinant 1 and over n by n, right? N by n matrices of determinant 1. That's also a group. So if you take a subgroup of a group, it is, and you have a topology on top, you can bring it down to have a topology there, and it's a group, so topological group, okay? There's something about closeness because Hausdorff. Hausdorff means, okay, if you take metric topology, you are fine. So now what we talk about is you have a group and you have group homomorphisms. Everybody knows what are group homomorphisms, right? So if you take T is a group homomorphism if T x y equal to T x T y, right? So for example, on real line, you have a linear map. So Tx is Rx, then x plus y will go to R into x plus y, which is Rx Ry, which is Tx plus Ty, right? So on Rn, all the n by n matrices are linear maps, right? So those are group homomorphisms. So GLNR defines a group homomorphism. So group homomorphism, which is also a homeomorphism. Remember, you have a topology, right? You have a metric space. So if you have a group homomorphism, which is continuous, invertible, and its inverse is continuous, then it's called an automorphism of this group tree, okay? So the map we took earlier for S1 cross S1, remember, RS going to RS, comma S, that one is a automorphism, okay? And any map in GLNR, if you take its action on Rn, right, n by n matrix will apply on Rn, that is a group homomorphism, and it's invertible, its inverse is continuous, and it is an automorphism, okay? So just keep that in mind. You don't have to know more, that if you are on Rn, you're going to take an n by n matrix and apply to it. That's your automorphism, okay? So an automorphism T of going from G to G is called distal. Of course, the definition doesn't change, but there is an equivalent condition that no orbit goes to identity because it is a homomorphism. So if I have orbit of 2 points which converge to same point, say orbit of x and orbit of y, then I can take orbit of x, y inverse, that will go to identity because group, the elements are invertible, right? And T is a homomorphism. So as long as your orbits stay away from identity, the map is distal, okay? So we study the dynamics of this, and I'll give you a glimpse of that in next 5 minutes, and then we'll do something else. I think I was given 1 hour, so I have enough time. So don't get scared by the maths part of it. It is, you know, when I was a student, graduate student, that is a PhD student at TFR, we would attend all seminars and we would only understand words in the beginning. Slowly you get to know what the person is trying to do. Slowly you understand what the problem, research problem is, and so on. But you know, you learn to get something out of a seminar. If you never attend, then you don't learn. So the point of the seminar is not that you will understand everything, but you get some gist of it, or you get few words out of it, or you feel good about it. That is what. See, these seminars when people give, they have worked for years on it, right? So it is not possible for even many senior mathematicians to understand everything, but you slowly learn to understand few more things in a seminar. That is the philosophy of a seminar, okay? So I am always talking about orbits, so I'm going to only concentrate on orbits in this part. There are many more things which people do, and I'll go quickly over this. So a homeomorphism T of X, a space X, is said to have minimal orbit closure, which is called MOC. If I take any orbit and its limit points together with it, then it should be a minimal closed T invariant set. See, orbit is invariant, so its closure will be invariant. And it should not have a proper invariant subset, T invariant closed subset. So MOC stands for minimal orbit closures. And homeomorphism T has MOC, then X splits into these components which are disjoint and T invariant, okay? And its T action on this is ergodic, means the orbits are dense in that. So let's talk about what is called distality and orbits, the relation. So if you have a group and automorphism T, then if it has MOC, then it implies distality, because these distinct orbits, they are minimal closed invariant sets, so they cannot go close to identity, because identity is also T invariant. Your map is a homomorphism, so identity goes to identity. So that, and it's 1, 1. So these maps cannot go close to identity. Identity is one component by itself. Now, does distality implies MOC? Yes, that's the thing, that distality and MOC are two equivalent property for an automorphism of G, which is now you have distinct ergodic components and you can study them separately. That is the point of this characterization. Now let's talk about these contraction groups in so you see you have orbits, and when you have map distal, then nothing goes close to identity. So you are taking x square, but there are other maps. We saw that Tx is Rx, where say R is half, then identity of group R is 0, and if I take Tx, half x, 1/4 x, 1 by n x, it goes to 0, right? So let's take this set, which is called contraction group of T. So all those x whose orbit goes to identity, okay? So for example, if I take Tx equal to half x in R, then this contraction group will be whole of R, okay? So that's because, so if I have Tx in Rn, if I take say Tx equal to half x in Rn, again the contraction group will be whole of Rn. So this is the subspace on which the eigenvalues are here. For example, it is half. So eigenvalues are less than 1. So of course you can have complex eigenvalues. So eigenvalues are of absolute value less than 1. Okay. Or so that's called contraction group. Okay. And you could also have eigenvalues greater than 1, then it is contraction group of T inverse. Okay. So if T is distal, no orbit goes to identity, so the contraction group is trivial, right? And also same thing for contraction group of T inverse. Now for a long time people are thinking that whether this is a sufficient conditions. So what about the converse? Can you characterize distality in terms of this triviality of these contraction groups? So it looks very simple, right? That you have that contraction group of T and T inverse are trivial. You want to know whether T is distal. And it was known for some, like, you know, compact groups or Rn you can see easily, but not in general for all locally compact groups. So yes, it is indeed in fact true that the contraction group of T is trivial and T inverse is trivial. Here there is a typo. See, T inverse is identity, then T is distal. So now I'll just briefly tell you a little more about this, and then we will have no more actual formal mathematics for the rest of the talk. Mathematics, but not, it'll be talked in general terms. So, see, I talked about one automorphism, but you can talk about a group of automorphisms. So if you have a group G, then you have conjugation action, X going to GX G inverse, right? So that's the homomorphism. It is actually invertible, right? Because X going to GX G inverse, the inverse is X going to G inverse XG. So these are homomorphisms which are invertible, and because the group already has topology, these are always continuous. So everybody knows conjugation. So inner automorphism means a conjugation by an element in G. So X going to GX G inverse is a conjugation map by element G on G. So these are automorphisms. When all these automorphisms act distally, then it's called a distal group. So G is distal if this orbit GX G inverse, this one, G belongs to G of element X, does not go to identity, does not go close to identity. And it's called pointwise distal if every inner automorphism acts distally on G. The whole group of inner automorphism may not act distally, but this means if I fix element G and take any X and take its orbit, then it should not go close to identity if X is not identity. For a large class of group, these conditions are equal. What is called connected groups, connected locally compact group, distal and pointwise distal groups are same, but in general they are not. So for example, if I take an abelian group, then conjugation action is a trivial action, right? Because GX G inverse is just X, so it's an identity map, right? So identity map is always distal because X and Y, the orbit is just X and Y, so it doesn't change. So abelian groups are distal and pointwise distal. Compact groups also one can check, they are distal, and nilpotent groups. So what are nilpotent groups? Okay, it's a group property you may not have come across, but if you take upper triangular matrices with diagonal 1, then those are nilpotent groups. Okay, so it's a group operation. You to take commutator group GG, then GG1 and so on, and it should reduce. So abelian groups, compact groups, nilpotent groups are pointwise distal as well as distal. And why do we study distal groups? Because so you can also talk about quotient. So quotient of pointwise distal group is distal. And why do we study this? Because you can study probabilities on groups and they have a certain behavior, and you can characterize behavior of probability measures on these pointwise distal groups. So there is a necessary and sufficient condition of if a group is pointwise distal if and only if the probability measures on it behave in a certain way. So they sort of either get concentrated or they dissipate and so on. So you can study probability measures on real line, on Euclidean space, on other groups and so on. So now I have finished the formal maths, and I hope you took some part. I'm going to talk about mathematics, but not technical part, really. So now like this comes to my later half of the talk. This is that. So I don't know if, but I think everybody would have seen a billiard table in a movie or online or. So this is a billiard table, okay. This is another version of that, and the stick is called a cue, and there is a white ball, and there are colored balls, and you hit the white ball to hit another ball to go into these holes. So it's a bit like carom. You play carom, right? Where you have a striker and you hit it, and those things have to go into these holes, right? So here, instead of striker, and these are balls, so they roll, and you have to hit. Carom, of course, is square and has only 4 ends. Here there are 6. So so sometime, like striker also, you hit a wall and then it bounces, right, at an angle and hits something, and then it makes it go, right? Sometimes you can't hit something straight into the hole. So like that, here also ball, sometimes you have to hit to a wall and it reflects back. This white ball you hit to a wall and then it reflects back and say hits this blue ball or dark black ball and it goes into the hole, right? So suppose I hit my ball, white ball, it hits here and it goes here and it hits and this ball goes into this hole, right? So try in carom, what you do, similar way you can play, right? So this is a billiard, and you think, what angle you have to hit to get some ball into that, right? So that's mathematics behind it. And there are models of mathematical billiard, which just follows the similar principle and then do it. So of course, you just hit randomly, things may not happen, right? So you have some strategy and you hit properly. So mathematical billiard is a dynamical system in which a motion of a particle alternates between straight line, like if you hit a ball straight, it'll go straight, right? And specular reflections from a boundary. So when it hits a boundary, it will reflect from it without loss of speed, and the angle of reflection is same as angle of incident, right? So you can see this. So here this is a stadium billiard. So you can have any shape, but this one is called a stadium billiard because it looks like a stadium, right? So you're going here, it reflects that angle of reflection, right? So so because it is reflecting back from a boundary, you can have what is called illumination problem, which is based on this. Basically, you can use this mathematical billiard. So imagine a room with mirror walls, and if you have a light going to the wall, obviously it will reflect back, right? So if a candle is placed at some location in the room, will it illuminate every other point in the room? As the light ray hits the wall, it reflects back at the same angle as the angle of incidence. So remember, when you put a light source, it's not like the particle, it is moving in every direction, right? The light is moving in all direction in 360 degree, right? And when it hits those walls, because room has a mirror wall, it will again reflect back, right? So the answer is yes, if your room is a square or a rectangular room, right? If I put anywhere, the light will go everywhere in that room, right? Because it's a square room. So imagine, put a light source, light will go everywhere, right? So what if the room has any other convex shape? So because you can draw in a convex shape a line from any point to any other point, so straight the light will travel on that and reach any other point. So in a convex room also this will happen. But suppose my room is not convex. I have an irregular shape room with, so the walls are not it's not square or rectangular or convex, or like we saw the previous one, which was the stadium shape. So those are all convex shapes, right? Circular is convex shape, but irregular shape. Will the light go everywhere? So this is a room designed by a famous mathematician, Roger Penrose, in 1958. So you see, the room is this part inside. here, all these, but this part is not there. There is a hole here and a hole here, where no matter where you place a candle in the room, there is a patch with positive area which is not illuminated. Okay, here the candle means you just have to take a point of light source, and the light travels in straight line, and when it will hit a mirrored wall, it will reflect at the same angle as the angle of incidence. Okay, must have done the experiments in your school about mirror and so on, right? So this is, it doesn't matter wherever I put the light source, it will not illuminate everything, and this is because of these, and he has proven that also mathematically. So there are other interesting examples. So this is a 26-sided polygonal room, and this right hand side is 24-sided polygonal room. Okay, and it has mirror walls, and if you put suppose this point is your light source and it's going in every direction, okay, then it will illuminate everything except this point. Okay, and if I put a light source here, then it will illuminate everything except the other point. And similarly this one, so these rooms were created by Tokarsky and Castro. So these are polygonal room with mirror walls. This first one has 26 sides, second one has 24 sides, and exactly one mark point is not illuminated by the other mark point. So if your light source is on the left hand side in the left one, then the same room, the one point will not be illuminated, and another, if I put in the second point, then the same room, the whole thing will be illuminated except one point, which you can, which they proved mathematically. Okay. So now, do people recognize this lady? Anybody? She quoted that the more I spent time on maths, the more excited I got. So her name is what? Let's see. Now, does anybody recognize this lady? So, okay. So she is Maryam Midzakhani. She was born in 1977, and unfortunately, she passed away at just the age of 40 in 2017. So Maryam was a brilliant mathematician from Iran. She won a gold medal in the International Mathematical Olympiad in 1994, and again in 1995, and with a full score that time. Her research work was mainly about understanding geometry and dynamics on hyperbolic surfaces. Okay, so I'll tell you what are hyperbolic surfaces. She proved several path-breaking results in a PhD thesis. Okay, she worked with Macmillan, and in her last few years, along with Alex Asking, she proved a famously known theorem called magic wand theorem, which led to resolution of various unsolved mathematical problems. And that's why it's called magic wand theorem, because it's like waving a magic wand and getting a resolution of problems, right? So that's why it's called. So dynamics on, so she studied on what is called dynamics on hyperbolic surfaces, and I'm going to relate it to illumination problem. That's why I talked about illumination problem, about these light source and mirror walls, right? So one example of a hyperbolic surface is the surface of a double torus. So this is a double torus. That one is called not double torus, just a torus. So you have two torus joined, okay? And it's obtained by identifying these torus is if you have an octagon and you identify opposite sides, I'll show you a picture, then you get this surface. So this is your octagon, and you can see different colors and A, B, C, D written. So A green side is identified here with A, B is identified with B, C is identified with C, orange, and this brown, D is identified with D. And if you look at, you can try doing it and you can see that, for example, the torus, earlier the torus, that is just identifying a square on opposite sides. So one side you get cylinder, and then you join back those other two sides, you get a torus. So torus you get from a square by identifying opposite sides. And this one, it's not exactly opposite sides, different sides, but you identify them and you get this double torus, okay? So you can also see online some pictures which tell you how identification will give you that too, if you want to study the geometry. So these dynamics of hyperbolic surfaces is studying dynamics on geometry. So double torus is a known example of translation surface. What is translation surface? It's a finite union of polygons with choice of identifying parallel sides of equal length. So here you see you have equal length and you have identified them, right? So you can identify and get this. So translation surface, so Lele, Montel and Weiss proved, drawing upon the work of Midzakhani, that for any translation surface M, there are only finitely many points in M which are not illuminated by a given point in M. The thing is that here, instead of straight line, you see you're in torus anyway, you can't go on a straight line. One has to consider light rays traveling along a geodesics. What is geodesics? Geodesics is the shortest path between 2 points on the surface. So you are given a hyperbolic metric, and you, depending on that, you have a shortest path between 2 points. Like in real Euclidean space, shortest path between 2 points is a straight line, right? In Rn, R1, R2, R3, if you want to go from point A to B, you can go straight line, right? Of course, in real life, if you have walls and so on, you have to go around. But imagine that it's an empty space and you're going from one point to other. It's a straight line is the shortest path, right? In R1 and R2, R2 straight line. Here you have to go along the geodesic. So it's not straight line. So do you know who these people are? So this is Maryam here with her daughter Ananhita. These are 2014 film medalists. So these four people, so the one on the left is Arthur Avila, who is Brazilian, then Martin Herer, British, Maryam Midzakhani, who is Iranian, and Manjul Bhargava, who is actually Canadian but is of Indian origin. His parents are from Rajasthan. So Fields medals are given to mathematicians under age of 40 and every 4 years in an International Congress of Mathematicians, which is held every 4 years. Next one is supposed to be in 2022 in Russia. Okay, this was in Seoul in 2014. The last one was in Brazil in 2018. So let me just wind up the talk. I have 2 more slides, and this is about Indian women in mathematics. It's where I am actively involved. So this is collective of mathematicians, not just women, who work to promote activities. So here is a website address. In the next page also it will be there. If you search for IWM Math, you will find this website. And so we are a collective of Indian mathematicians that has been in existence in 2009. Our mission is to encourage more women to pursue higher education in mathematics and organize events and networking opportunities that will enable them to take up a research career in mathematics. And this is the website. I'm sorry you can't see all of it, but it is last word is IWMMATH. IWMMATH. In the previous one also you saw here at the bottom, IWMMATH. Okay, so if you search for that, you will find. And so this is, so I missed one map I had of activities in India, which I missed, but we hold 3 activities, 4 activities actually. One is our annual conference where masters, PhD, postdoc, and faculty and teachers and all can apply, register, and attend, which would be in January for this financial year. Then we have a regional workshop for masters and onward students, which is in Patna this year, and IIT Patna. And then, so more, this year all the things are online. Okay, and then we have these visitors talks, which earlier used to be outstanding women and mathematicians from India and abroad giving talks in various remote areas of India, like not just metro cities. And that was to popularize and encourage women to take up mathematics at higher level. And they worked as the role model for them. They would give semi-popular talks. And the 4th activity, which is relevant to you, which is a workshop for young women in mathematics. This time it is in IIT Kanpur. And if you go to our website, soon there will be an announcement, and I will also share with Professor Sarkar. So 2nd year students of mathematics, women students can apply and take part in it. And we will, and I mean, you can apply and register, and then there will be a shortlisting and so on. So that's 1 week workshop, and I encourage girl students to take up and take part. Thank you very much. These are some references. I talked about these Maryam Midzakhani's work towards the end. That is mentioned in this popular article in Resonance, and it's free journal online. You can. It's written with Nikita Agarwal and Geeta Venkatraman. You can have access to that. And there is also another special women's issue of Resonance, which has some interesting math article about prime numbers and other things which you can have. Also, it has an article in applied maths, mathematical biology, where applications are to growth of cancer. So you might be interested in reading those articles. These are free online Resonance issues. All Resonance issues are free. So if you find math article, they are accessible by college students. Thank you very much. That's it.
Thank you, madam. If anybody has any question, can we start now? Question session?
Sure.
So if anybody has any question, please unmute yourself and you may ask a question to the speaker. Madam, I have one question, that periodic orbit and dense orbit regarding.
Yeah. Tell me.
Yes. Then, so if you just go to the, is it possible to go to the slide?
Yeah, sure. I will go to that. You want to go to that unit circle or where? Just tell me when to stop and I will.
Yes, unit circle.
Yeah, okay.
Yes. Is it? So, so dense orbit means the.
Yeah.
So you just tell, if you just will again repeat what you have told.
Yes, so you see, if I take say 60-degree or 90-degree rotation, I'll come back to the same point after some time, right? Because when it becomes 360, I'm back, right? But if I take a rotation which is an irrational angle, means say r pi, where r is an irrational number, then no power of that will become 2 pi, right? Because, I mean, no multiple of that becomes 2 pi, right? So the point is where I start, I cannot come back to that point. And it's slow, then you can show easily, like if you take in 0, 1 a rational number, and you take its add up. So say r is a rational number, r and 2r and so on, 3r, 4r, and modulo 1, you will see that it's dense in 0, 1, because no multiple of irrational number is a rational number, right? So you can, there are easy proofs of that. So this is a picture, heuristic, but you start with any point, and it's like if you're in real line, you start with an irrational number, and if I take, say, r, 2r, 3r, 4r, I will never hit an integer, right? If I hit an integer, say nr equal to k, then r becomes k by n. So I cannot hit an integer, right?
Yes.
So if I take modulo 1, that means that I'm in 0, 1, and it becomes dense in 0. That's one.
Thank you.
Yeah, I mean, if you want proper maths proof, I can also send it to you. Like.
Thank you.
Yeah.
Please send me.
Okay. So rational periodic orbit is like, so this is 90 degrees, so it is pi by 4. So pi by 4, then pi, then 3 pi by 4, and 2 pi. So when you take 2 pi rotation of a point, you come back to the same point, right? Yeah.
So if anybody has any question, so please ask.
Hello, ma'am.
Yeah.
You give a map on torus. T of r comma x is equal to rs comma s.
Yes.
And you told that this represent the twist on torus. How?
Yeah, it's not a twist in that sense. So you draw a line on the so torus, for example, I will show you this. So this torus, you take this great circle around it like this, okay, around, not inside out but around, okay. Now this circle, if I apply T to this circle, then it would go around like this, and it go out, go down, and go. So your torus does not become like that, but when you take a circle, it is going around. So suppose I cut the torus and join back after giving it 360 degrees. So when I cut it, it's a hollow pipe, right? If I cut it, it's a hollow cylinder. Sorry, So hollow cylinder. Now I twist it, and so it's a long hollow cylinder, whatever, and then you twist it, and from one end you keep same, other end you twist it. Finally, it is total 360 degree, and you join it back. Then that is what I meant by twist. It is not the torus remains a torus, but if you want orbit or T of one circle around, then it goes out here. From here it will go to 90 degrees, here it will go to 70, and so I can't draw it, but imagine I had a circle around, and what happens when I apply T, and that's what happens. It looks like when I have cut the cylinder and twisted it by 360 degree and joined back, that is, and then I look at that line around it, how it looks, that is what I meant by twist.
Okay, ma'am. Thank you.
Yeah. Anybody else? Feel free to ask any question, math, non-math, no problem.
Please ask question if anybody. Debarmita Chatterjee. Hello, can you listen?
Sir. Yes, sir.
Yes, please introduce yourself. You ask one question.
I am Devomita from JNU. I'm a PhD student.
Oh,
I'm now working on Distilled Action.
okay,
I'm a
fine.
student of Riddhi ma'am.
Thank you.
Actually, she's just starting, so she decided to attend the talk so that
Fine, fine. Okay.
It's our great pleasure, ma'am, because the scholar and the students both are with us.
she's from Calcutta, so she's in fact
Her name suggests so.
yeah, and she's
Chatterjee.
currently at home because of pandemic, and so she works online basically.
I personally will follow the resonance and I'll ask my students to follow the
Yeah.
journal.
There is another volume called Lilavati's Daughters, but I think now it is not online. So that's a journey of women scientists in India, again published by Indian Academy of Sciences, and it is about 100 essays written by women scientists, different scientists about their experiences. So there are mathematicians, physicists, chemists, biologists, medical.
Would you please repeat the name again?
It's called Lilavati's Daughters.
Lilavati's Daughters. Okay.
So from where can we buy these books, madam?
Yeah,
From
it's
anywhere.
available. Indian Academy of Science has a website, and there the address is given. Phone numbers are given. You can ask, talk to them, and they can deliver it. It probably costs 300 rupees. I forget now, but it used to be cheaper actually. So maybe it is cheaper. I don't know, but not more than 300. Maybe 150, 200. I don't know.
So Arindam, we can give actually in our prize books we can include this book.
Yeah,
Exactly.
Lilavati's Daughters would be great. I will send you some link where to buy. There's also
Okay, thank you,
Scholars
madam.
Without Borders online where you can order also. I will find out and share with Professor Sarkar.
Thank you, madam.
Okay, ma'am.
Yeah. So that might be good for girl students to read. Yeah. So
Especially
it's very inspiring essays about their journey, what they faced, hurdles, sometimes family also does not want. Though in Bengal, I find that people are more, they appreciate education more, unlike in many other parts of India. So, and everybody enjoys education, and girls are also studying well and so on. I find lots of people, lots of girls. So, for example, TFR has one program every Sunday, Chai and Why, where students can enroll. Maybe I'll share that site with Sarkar.
please do.
Professor Sarkar, you can.
Yes.
So anybody, any student or anybody can join, and they talk about science in layman's term, and they try to reach out to college students, and so even school students sometimes join.
Oh, fine.
So those are really lovely, and most of them, many of them are done by PhD students, and some are done by also faculty. They show you different things, like even mathematics has program, physics, chemistry, biology, about their research and so on. They are beautifully done and students enjoy. Sometimes I attend, it's usually on Sunday, and so if I'm not busy, I attend those programs, though they were meant for students, but I enjoy them. So.
Madam, I'm Sajal Biswas, Assistant Professor of Physics of Krishnagar Women's College. I have one question.
Yeah,
Madam, is there any relationship between torus and saddle point?
They have a different geometry actually. So torus is smooth surface, right? Saddle point is not which also has hyperbolic. So no, they don't. They have a very different geometry.
Okay. Thank you.
But, so you study hyperbolic geometry where saddle points appear, while just a torus will not have that. But there are, if you take double torus and then, I mean, if you take different geometry, then you will get, but not on torus. This is torus, no. So there is no. This is smooth surface. This is a Euclidean geometry surface on it. You need a double torus to get to the surface, which I talked
The
about.
twist to get a saddle point, ups and downs in the saddle point.
Okay, yeah. So the twist is very misleading here. Actually, twist was just to show an orbit of to show an operation on a circle, but this surface is completely smooth and there is no saddle point here.
Ma'am, is dynamics and the modeling of the dynamics model, are they related somehow? Are they related to the stochastic process?
Yes, stochastic process is also.
It is a great use in dynamical models, no?
Yeah. Stochastic processes are also very useful. And in fact, in economics and all, they do stochastic processing. So I worked earlier on probabilities, but again, I do pure maths, but it has certain problems are related. So dynamics has a lot to do with stochastic processes and vice versa. See, dynamics is not one thing, right? It has, I mean, as I mentioned, it's anything, study of anything which, so dynamical behavior of various things you can study. So
yeah, you have mentioned the focused of weather report,
yes,
which is basically a stochastic. I'm from statistics.
Oh, so, I see. Okay.
So basically, the stochastic models are used to weather forecasting.
Yes. So that's very important.
Somehow they are related. Yeah.
Thank
you, ma'am, for this very inspiring lecture. And actually, we are going to establish a Women's Studies Center in our college. And if necessary, sometimes I will call you or I'll send you mail regarding the advice. Because basically, the Women's Studies Center are basically based on social science subjects.
Yeah.
But here, you have started, actually, you have shown a path where the mathematician or particularly the women scientists, they have a very encouraging involvement in the
let me mention one thing I forgot. All our activities of Indian women and mathematics are supported by National Board for Higher Mathematics, Department of Atomic Energy, Government of India, NBHM. And they also have, we have small component of funding, very small, comes from International Mathematical Union Committee for Women in Mathematics. But that's very small. More like 99% of our funding comes from NBHM. And it's actually started as initiative of NBHM. So they fund everything that we say. And they want to promote women in mathematics. They want women to take up career in mathematics because the proportion of women as mathematician and also teaching is very small. It's like 15% kind of most places, and in research institute is even lower. So some institute in fact have zero also. So they want to promote women mathematicians, women students.
If I'm not wrong, that JNU it gives 5 additional credit for the girl child. In the admission process.
Yes. It's for not for PhD anymore because UGC made some rules, but for master students they do. Yeah. And also MPhil is probably going away, but MPhil students, master students, and they did it for. There are some undergraduate programs in JNU like languages and all. So they also give 5 points to girl students, every girl. So like exam is 100 marks. And whatever marks people get, if somebody is a girl, then 5 marks are added. But not only that, if you are, so whole of India is divided into different regions. And So like non-metro rural areas and all get 3 points, 2 points, 4 points. And if you have done your if you have done your previous degree in one of these places, then you get those points also. Because you see, if you study in like place like Delhi or Bombay or metro city, you have more exposure. You are, you get more. You become, let's say, maybe you are good at expressing yourself, but people from rural areas will maybe smarter, but they don't have that exposure, so they may not be able to do as well in the exam, though some of them do very well. So they give, just to bring them on par, they give this points, and this is all done centrally. We have no idea who comes with what and all. So we have a lot of students who come from rural area, and I see that first year they don't express first semester, but by the end of fourth semester, they are like, you can't tell the difference who is from where. So it's like equal opportunity initiatives.
Yes, it is. It is actually they are trying to introduce equity instead of equality.
Yes, equity, just to bring people at par. See, because exam is not everything, right? So we have to take exams because we have a lot of applications, and few seats, but that's giving equity, basically bringing equality between people and giving chance to
bring the people in the same platform.
Yes, and give them a chance to learn, because otherwise, only few people will get admission, and then there will be same people. And I mean, I find that very good in JNU.
Thank you, ma'am.
Madam, one question more, that why you have studied mathematics?
Very fantastic question.
So, well, I mean, for me, I just loved mathematics. Even as a child, I loved mathematics. But, okay, so I also have an essay in this Leelavati's Daughters. So my father was a civil engineer, and I always looked up to my father, and I always wanted to be an engineer. But my mother told me that since I love mathematics, I should pursue mathematics. And it's true that, in school I was kind of always going late and all. And then, but if first time I realized that I can go extra late is when my maths result came, so that teacher won't punish me. So, but I loved mathematics, and that is the only thing I think I can't live without mathematics. So for me, if I have any other trouble, I do mathematics to get out of it. I mean, I get absorbed in mathematics, I forget everything else. It doesn't matter what it is. Life can go on, and I am in my mathematics. So my thing is, I love mathematics and I'm in it. So that's it. Yeah.
Fine.
So it's right. Okay. So I had a lot of encouragement from my parents, and they always supported me. And in fact, even after marriage, my husband and I had to stay in different cities, but my in-laws were also very supportive. They are from Calcutta, and my mother-in-law was a school teacher in Barasat. There's one girls' college school which is like 150 years old. I forgot the name. But she always supported me, though I was staying in Bombay and my husband was staying in a different institute in Allahabad. But she never said like that I have to be with my husband. Some of my relatives did say that, but not them. My in-laws were very supportive of saying that I have my own career and my own research. And I had a small child that time and was with me. But so that was not an easy life, but they at least understood the importance of an education career in education and research and teaching. So very progressive, I must say, which is a thing I found in many Bengali people. So I find that they are very progressive compared to many other places in India. So the girls in Bengal in your college have a lot of opportunities and they should take it, you know. Nowadays, there are a lot of other attractions like cell phone, this, that. But imagine you can find information so easily, so you should put it at good use, right? Earlier, it was not like that. So everything you want to know, you can search and find, and you can also have access to research papers easily, and it's not difficult to learn things. Of course, you have to learn to shift it through to see whether what is right or wrong. Sometimes there are wrong informations online, but you can learn and on your own also. So, and mathematics is something you don't need much resources, right? You need paper and pen, and you only need your brain, right? You don't need like labs. So it is well designed for women to do mathematics. They can do things for their family as well as they can do mathematics anywhere.
Sure. Is there any more question from audience? If there is no more question, then I request Dr. Maya Biswas, HOD Chemistry, to propose the vote of thanks. Maya Madam, hello.
Hello.
Arindam, hello.
Do you ask him?
Maya Madam.
Maya Madam.
Yes.
Yeah.
Yes.
Okay.
Yes. Maya Madam, are you audible? Can you hear me?
Yes. Am I audible?
Yes.
Okay. Good afternoon. I am privileged to get an opportunity to give vote of thanks to the dignitaries, distinguished guest, respected speaker, president of governing body and principal of Krishnagar Women's College, and my dear students. At the outset, I take this opportunity to extend thanks to the mathematics department, Dr. Arindam Sharkar, HOD, and Dr. Snehadri Shekhar Mondal of our college for organizing such a very good seminar lecture on the topic Glimpses in the World of Dynamics. The seminar is extremely important and relevant to the teachers and the students to get equipped with the latest trend in mathematical sciences. The college is very grateful to the famous mathematician Dr. Riddhi Shah, professor of mathematics, professor of mathematics, School of Physical Sciences, Jawaharlal Nehru University, New Delhi, who despite of her busy schedule has taken trouble to address the seminar for enlightening us. She has lucidly expressed the complicated aspects on glimpses into the world of dynamics in all fields of science and in our real life also, and especially emphasizing the pioneering role played by the Indian women, also the women abroad. Thank you, ma'am, for your nice and wonderful presentation. I convey my gratitude to the Honorable President of governing body of our college, Dr. Monojit Ray, to remain present in the seminar. He also enlightened us about the need of updating knowledge on various subjects in tune with the changes taking place in the society. It will not be out of place to mention that Dr. Natasa Dasgupta, principal of Krishnagar Women's College, greatly inspired us to hold the seminar for the benefit of teachers and students, and emphasizing especially today the applicability of the topic in real life. We are grateful to our distinguished guests, dignitaries, and the teachers of our college, especially to Sajal Biswas, Department of Physics, spending their valuable time in holding the seminar successful. Last but not the least, the dear students who participated in the seminar made it very successful deserve special thanks. Thank you all. Have a nice day.
Thank you.
Thank you.
Thank you, madam. So, should we conclude now?
Yes.
Yeah.
Yeah. Thank you.
Thank you. Thank you,
Okay.
everybody.
Thank you all. Thank you.
Okay. Thank you.
Thank you, ma'am.
Bye.
So we can leave now, Arindam?
Yes,
Can
certainly.
we
Yeah,
leave?
sure.
Okay.
Yes.
Thank you.
Okay. Bye.
Ma'am.
Bye. Thank you. Bye.
Looking forward towards the kind cooperation, and actually, of course, we'll keep in contact.
Okay.
Sure, sure. I'll do whatever I can. Okay. Bye. Nice meeting you all. Bye. Thank you. Thanks for inviting me. Bye.
Thank you.
Bye.
রেকর্ডিংটা বন্ধ করবেন এবার অনিন্দম দা।
হ্যাঁ